So I'll be talking about towards high performance machine learning on the edge. We have a lot of data. As machine learning scientists, data scientists, we're dealing with data all the time. We can kind of data back to the internet era, the 2000s, when we started collecting all this user-based data based on how people were using the internet. And at that point in time, users typically had one device, which was a laptop, maybe, but more often a CPU or a computer. Now in 2010, that's when mobile computing sort of started coming up, and that included things like laptops, mobile phones, and tablets, and that produced a lot more data. In 2015, there was a lot of work on social media, and it's still continuing on. None of these things have gone away. They're still part of this whole big data framework that we have. But yeah, in 2015, that's when a lot of the researchers started focusing on social media data. In fact, even I was working on Instagram and Twitter data at that point in time. And then looking at now, we're looking at Internet of Things, drones, gaming, VR. So the key idea is that the nature of the data is consistently shifting to being more real-time, more personal about the environment. And the availability is consistently increasing as well. So what do we do with all this data? And it shouldn't come across as a surprise. We are trying to use this data to learn behavior about the environment or behavior of multiple users. And deep learning is one way to do that. So deep learning allows us to solve complex nonlinear problems using large amounts of data. And because of the hardware technologies that have provided us this capability, and again, increasingly available data, deep learning is very appealing. Now, I do want to point out that I'm not suggesting that we use deep learning for everything. In fact, I'm actually opposed to that. I think deep learning should be applied in the right applications where it is actually necessary, not just plug it in everywhere you think you have data. So what does a deep learning pipeline look like? And I'm sure all of you guys know this. I'll just quickly go over this. There's a deep data pre-processing step where you're ensuring that the input is in the right and consistent format. Then you have the model training step where you are collecting, or where you're selecting the model to use along with parameters and hyperparameters, and then you end up actually training your model. And lastly, you have the deployment stage where you can deploy your model in a lot of different domains, including here I've put things that I'm interested in: mobile computing, Internet of Things, cloud computing. And these are more so the modern day systems, as you would call it. Now, one thing I do want to note is this deployment phase of machine learning. So deploying machine learning models is not as often looked at from a system standpoint, people that are working in these areas. And so that's what I am looking at. So let's look at what modern day systems actually look like in a little bit more detail. So I talked about mobile computing, and mobile computing is basically a distributed system which is connected via wireless network, and it's, that's how it's communicating. The main characteristics are the fact that it has mobility, the fact that you can carry your device with you. You have your cell phone or your smartwatch or your tablet, you can carry these things with you. So mobility is a big thing. And then the second thing is the ability to provide computing at anywhere and any time. So you have everything literally at your fingertips. And then the second modern day system that I'm looking at is the Internet of Things, which is basically a network of physical objects called things that are embedded with sensors, software, or other technologies via, again, wireless networks. And these range from location fixed devices, such as anything in your smart home, for instance, a smart thermostat or a smart light bulb, to wearables like smart watches and health monitoring devices. And fun fact, these are expected to surge to 150 billion by 2025, which is a pretty big number. So what are some characteristics of these? One, they are connected via wireless networks, which is, that's how they communicate. And I would say they're more connected than ever before, because now you have like the Internet of Things is also communicating with your phone. You can do a lot of things with your phone. And so there's inter-cross communication, essentially. Secondly, they're distributed in nature. So the fact that when they're communicating with a centralized server, they're distributed, that's distributed. It's not happening just on the local device. And they're also distributed in nature in the sense that they're communicating with across devices. And lastly, and probably the most important to us, is that there's continuously streaming data. We're looking at more real-time, more continuous. So how is machine learning used in this
I have
context?
a question.
Oh yes, go ahead.
In the last slide, you said if they are distributed, but most of the current like IoT thing, they are always, you have a center cloud which basically, so the data is always collected on the edge, which is there, but the main processing and everything happen on the cloud. So are you saying distributed in terms of processing, or what's the meaning of distributed in that sense, like here?
Right, that's exactly right. Yeah, so distributed in terms of processing, how it's processed, and it'll make more sense when I move forward why I'm making that point. But yeah, distributed in terms of processing, but at the same time, distributed in how it's communicating with other devices. Okay. All right. So how is machine learning used in these modern day systems? So say you have a bunch of devices, and of course there's a centralized server, a cloud or data center. And the idea is that these devices collect information and transfer it to the cloud. Now, what the cloud does is it processes this data, often using machine learning or some data analysis, data mining, and offers back some type of service. This is how traditionally it's been done for, a decade, more than a decade. But one thing to note here is that as the more and more the data is becoming real-time, continuous, there is a low network latency requirement, which makes offloading intelligence to the cloud a little bit undesirable. If there's a way that we can avoid that, do some computation maybe closer to the device itself, that would be better. And then, of course, there's a lot of other issues, including privacy and security, with putting all this private, personal information about your environment on the cloud. So these lower requirements have actually resulted in the emergence of edge computing, which basically brings computation closer to the device. So the idea is that you have devices, you again have your centralized server, but there's this middle layer, you can call it edge nodes, or that's where the edge computing is happening. And the idea is these edge nodes can take care of certain computation tasks. Now, because these edge nodes the idea is that this graph doesn't do justice because these edge nodes are actually closer to the device than they are to the centralized server, so they're not right in the middle. They can take care of certain computation tasks that aren't highly or that aren't expensive because of the fact that they're actually located very close to the device. Now, if we do that, if we put some computation on the edge, that does result in low latency. There's a higher throughput and privacy and efficiency, obviously. So the recent development of low-end edge hardware like NVIDIA's EGX and Apple's Neural Engine has actually provided a path for doing machine learning on the edge. So for instance, my iPhone actually has a neural engine. I have one of the newer ones, and I can do machine learning on my phone, which is super cool. So this raises an important question. How can we design, develop, and evaluate high-performing machine learning algorithms that are accessible and scalable in edge environments? Now, what do I mean by high-performing? I mean a lot of things, which is it should be generalizable, explainable, fair, privacy-aware, data efficient. I'm sure you get the point. A lot of the good things, basically moving machine learning beyond predictive accuracy. And we're also looking at doing this on resource-constrained environments, like maybe on the edge, closer to the device itself. So the goal is to move towards low resource ML. And my work seeks to make machine learning more available, usable, and scalable for applications in edge systems such as IoT devices. So the rest of the talk, I'll be actually talking about two aspects of high-performing machine learning: explainable ML and privacy-preserving ML. And then I'll conclude the talk with a little bit on a future of ML and modern distributed technologies and a conclusion. So let's talk about explainable ML. So assume you have a autonomous vehicle that needs to provide instantaneous low latency decisions to the user or to the car to move forward. And say it uses a deep reinforcement learning agent to do that. So to give a quick summary on deep reinforcement learning agents, the idea is that there's a deep network and it's put into the typical reinforcement learning framework where the deep network is given the state and reward, the state of the environment and a reward function at each as input. And then as output, the deep network will give you an action to take. And that action is plugged into the environment, and based on that, you get a new state and new reward, and it's basically sort of a loop, and so it happens continuously. So in the case of autonomous vehicles, you have camera sensors on a car. So the camera sensors can send images to this deep RL agent, and it can get instantaneous low latency decisions. So say it sends this image of the road, and the deep reinforcement learning agent tells you to swerve left. Now, let's look at what's happening here. The image is a little bit small, but as you can see, probably the road is fairly empty. There's nothing in front of this car that is being, say it's the autonomous vehicle, but the agent still says swerve left, which can be a little bit confusing to either the user co-operating the vehicle. And so why is it saying swerve left? That's an important question to answer. Now, it could be because the deep RL agent is not doing the right thing, or it could actually be that this lane is closing, so it wants it to switch lanes, right? So now the idea is that these decisions, if they're explained to the users cooperating the vehicle, is just much better because we understand the reasoning behind this. So as AI-driven systems gain prominence in things like autonomous vehicles and health domain and smart cities, it's very important that these things, the behavior of these models is explainable for enhancing trust and clarity. So how do we explain deep RL agents? So since the RL agent takes as input images and videos from a camera sensor in the car, one can employ saliency maps, which is a popular visualization method to explain the agent's behavior with respect to the input. So this image that you have on the screen is a saliency map. It looks like a heat map and it's basically highlighting the important parts of the image that the agent used to make its decision. So in this case, the agent was looking at the two cars in front of it. Now, the idea is that this image is then used to explain the agent behavior, not just discuss focus. It's used to explain that it's looking 100 or 200 meters ahead of it, and that's how it's making its decision. Now, the question here is, how well do saliency maps actually work? Because as you can see, this agent is actually focusing right at the front, but it's not looking at the car that's entering right in front of it, or the truck that's entering. So how well do saliency maps actually work? So despite their usage, their common usage to explain agent behavior, it's unclear whether they provide useful explanations. So let's take another example of focusing on the context of Atari game Breakout, which is a common deep RL test benchmark. This is a saliency video of a deep RL agent playing Breakout. Here the agent is the paddle and it's controlling the ball to hit the bricks. So for RL systems, saliency maps are often used to assess an agent's learned representation and behavior over multiple frames, and hence you have this video. So for example, now note the high salience on the missing section of bricks, it just went away, which is popularly known as tunnels. So this missing, the idea is that because the bricks at the top are worth more points, if you make a tunnel, it's better for the agent, or it's better for you as a player. And so we saw, let me play this again. We saw that there was a high salience on the missing section of bricks. Now creating this tunnel to target bricks at the top layer is actually one of the most high-profile examples of agent behavior being explained according to semantic concepts. Now let's look at it a little bit deeper. I just took a little one of the frames from here. So given this intensity of saliency in this image A, it may seem reasonable to infer that the agent has learned to aim at tunnels. If so, if so, this should be the case for all tunnels across the game, right? However, what we try to do in B is we intervene on the ball, paddle, and brick pattern by reflecting it across the vertical axis. So we just swap the frame. And we notice that the saliency around the tunnel is not symmetric in the reflection intervention, which indicates that the hypothesis actually doesn't hold for all tunnels. It may just hold for the tunnels on the right-hand side, but we don't know that. And the idea is that our original hypothesis is incorrect. So despite their common use to explain agent behavior, again, it's unclear whether they provide useful explanations. So this brings me to our first work, which is Exploratory, not Explanatory, Counterfactual Analysis of Saliency Maps for Deep Reinforcement Learning. And this was presented at ICLR 2020 this year. And the contributions are that we provide a survey in how saliency maps have been used as evidence for explanations. We describe a new interventional method to evaluate those hypotheses, and we experimentally evaluate how well saliency maps provide inferences in deep RL. Any questions so far? Okay, I'll continue.
Yeah, can I go? Okay.
Yeah,
I was asking, so is it something like adversarial kind of examples where you are saying you are finding things which actually when change, but it in a meaningful way, it's basically the model is not able to do well in those cases. So I also want to know, is the model able to excel in that situation when you flip the things, and then is the model able to do good, or it's not doing good also?
So yeah, that's a good question. It depends on the game itself. For instance, Breakout, deep RL agents can really play Breakout well. Like they do it really well. And so I think at one point in time, somebody even said it's better than a human. I don't know about that. I'm not making that claim. But so it still continued to do well. It's just that the saliency map wasn't showing that. And what ended up happening, actually, if I remember correctly, was when we flipped it to the left and continued playing onwards, it, for some reason, just kept bringing the ball to the right side again and again. It didn't even, either, there's other hypotheses for that. Maybe the agent didn't learn to play on the left-hand side. And so the question here is, do saliency maps actually give you appropriate explanations?
And you flip in between, like, of the game, or you started with a broken bricks in one side, like left side, or you flip in between?
No, we do flip in between, yes.
Okay.
Yeah.
That makes sense. Okay.
All right. So we first present a survey of usage of saliency maps in deep reinforcement learning. This table presents a summary of 46 claims drawn from 11 papers, and we surveyed a total of 90 papers altogether. And the rows here represent categories of saliency map methods, and we look at 4 different methods. Jacobian is your typical gradient-based saliency map. Perturbation is more so you're perturbing parts of the image or masking them. There's also object and attention. I'm not going to go into the types, but we look at 4 of these. And the columns here present categories of their usage. So all 46 claims interpret salient areas as a proxy for agent focus. So for example, a claim about a breakout agent notes that the network is focusing on the ball and paddle and little else. And that is normal, right? That is just like saying, oh, look, the agent is looking there. 40 of these claims reason about what learned representation may have jointly produced a saliency pattern in agent and agent behavior. So the idea is that they're explaining using that focus that you see. So for instance, an agent learning to recognize a tunnel resulting in salient bricks and targeted maneuvering of ball and paddle. So you're associating the saliency on the bricks as, oh, the agent is learning to recognize the tunnel. And that is a possible behavior, a possible learned representation. But we don't know if that's true. However, only 3 of these claims are actually accompanied by additional experimental evidence, such as intervening on tunnel location. So out of 46, only 3 of them actually experimentally evaluate. We also noted some pitfalls in current usage, one of them being subjectivity. And actually, recent critiques of machine learning have noted a tendency to combine speculation and explanation. Saliency maps actually aren't designed to formalize abstract concepts. For instance, in this case, we have a frame of a saliency map, and say we have 3 different people looking at it. The explanation can be very subjective. The interpretation can be very subjective depending on who's looking at it. Someone can think, oh, look, the agent is aiming at tunnels. Someone can say it's targeting bricks closest to the ball, or someone can say the paddle is always salient. It's very subjective. And so how do you come up with explanations from something like that? Secondly, a lot of these claims were unfalsifiable. The main idea here is that a claim's falsehood should be identifiable from some experiment or observation. If any scientific claim, that is every scientific claim should be unfalsifiable, essentially. So if we look in this example, a diver is noticed in the saliency map but misunderstood as an enemy and being shot at. How do you actually falsify an abstract concept such as misunderstanding? How do you evaluate that? And lastly, there's cognitive biases. So researchers have expectations of how salient regions map to semantic concepts and how the semantic concepts map to high-level behaviors. And this imposes a strong cognitive bias in both the existence and nature of these mappings. For instance, we recognize a paddle, ball, and bricks and behavior like aiming and channel building, but to a deep network, it's not necessary that it learns these same semantic concepts. So in this work, we present a causal graphical model of the relationships between an RL agent and in the yellow plate and an image-based environment in the blue plate. So let's step through this together. So the environment, which is the blue plate, maintains some usually latent game state, which is transformed using some function f into a pixel representation. And that is what we see. We see this pixel image, and that is what the agent also sees with just the pixel image. But there is some underlying generative process that's generating this from game state. So game state could be considerate, for instance, a JSON. Whoever designed this game, it could be just a JSON, which links, okay, how many bricks exist at this point, what's the agent's location, what's the ball's location, things like that. But when you convert it into a pixel representation, we only see an image. The learned network, and then in the yellow plate, we have the RL agent. So that has, say it's a learned agent, it has a learned representation that it learned. And this learned network takes this pixel image and produces logits, which is then used to take an action. Now, temporally extended sequences of this action, if you do it over multiple frames, that action selection procedure results in what is called behavior, agent behavior. So now let's look at this. So what saliency maps are actually doing, and this is with all of them, basically the saliency maps are intervening on pixel state. So M here represents an intervention made by saliency maps. And the idea here is that these interventions are not naturalistic and they're inconsistent with the generative process F. So I'll give you an example for that. Say you have an example of a bird, image of a bird. And to get the saliency map to see whether the saliency map is looking at the eye, you mask the eye with some gray box or something, and then you see how the agent performs. But that is not naturalistic. The agent has never seen an eye with a gray box. So it's not going, so it's not going to work. It's only looking at pixel level intervention. Now that's not a problem. The problem is that researchers are making claims that correspond directly to game state. So humans make semantic concept level claims about agent behavior, and saliency maps are only doing pixel level interventions. So we can, then in that case, pixel level interventions are unlikely to be sufficient to explain these semantic concepts. Does that make sense?
I have a question. So why we are going through pixel level? Why don't we, like, if the game can be broken down into semantic concepts like ball, number of bricks, each side, their location, for example, let's say, rather than pixel level, then why can't we use that representation directly and without going through pixel level stuff? Why do people follow this? Maybe I'm new to this field, but still,
no, It's a good question. And that's exactly why we wanted to do this paper as well, because everyone was looking at these pixel level changes. And one of the problems with doing the semantic concept level interventions is there's not enough systems to allow you to do that. A lot of these images, we snap a picture on our phone, we don't have the underlying generative process of how nature is forming, right? And so someone has to go make that. Same things with games, with Atari games. We see the game, we can play it on our own, but we don't see the underlying JSON file, for instance, or the underlying dictionary that maintains all these concepts. So that's one of the problems. And in this work, in fact, that's exactly what we're proposing to do. We're proposing on intervening on game state to evaluate those hypotheses. So we're not saying change the saliency maps because there's a whole load of saliency map methods. We're saying that once you make those claims, we can test them by intervening on game state. Through this, and I'll talk about how we do that, but through this, we can verify whether counterfactual states produce expected patterns of saliency on the same set of semantic concepts. And that way we'll know whether the agent has learned a representation R.
Okay. So is it, you are saying that it's easier for to analyze kind of a pixel level stuff going through that frame, but to evaluate whether our hypothesis on the pixel makes sense, we can do some intervention on the game states.
That's right. Yeah,
Okay,
that's right.
Cool. Now I got the problem. Thanks.
Awesome. Are there any other questions? Okay. So yes, that's exactly what we're recommending. We're recommending that we should intervene on game state to evaluate those hypotheses. We're not saying we have to change anything at this point, but just when you make when you come up with these explanations, we should test them because these are hypotheses. They're not, saliency maps are not giving us direct explanations. So to do this, to intervene on game state and test hypotheses, we actually use this framework called Toybox. This was implemented in my lab. It's a set of fully parametrized implementation of Atari games. And we use that to generate interventional data under counterfactual conditions. So it's a very neat paper. And I hope it's one, first of many that allows us to do more testing like these. We also provide a framework for generating hypotheses that assist in designing more specific and falsifiable explanations that you can actually test. So concept set X is salient. If concept set X is salient, then the agent has learned representation R, resulting in behavior B. Now note that representation R is what we're trying to infer because we don't know that. X and B are things we can observe over multiple frames. So let's look at a case study, going back to the very first example that I presented. Bricks are salient implies that the agent has learned to identify a tunnel, resulting in maneuvering the paddle to hit the ball in that region. Now here we have that the top and the bottom image contain reflections of ball and paddle under the same tunnel configuration. So we just have, it's the same tunnel, the ball and paddle are just one on the right, one on the left side. Now, to evaluate this hypothesis, what we do is we intervene on the state by translating the brick configurations horizontally, so moving it across the board left and right. And what we see is when we shift it to the right, we see that the saliency pattern holds. The tunnels, there's still saliency on the tunnel. So our hypothesis is correct so far. It works for the right side. However, salience on the tunnel on the left side is less. In some points it's even non-existent. So very interesting that this happens, and we can come up with more hypotheses based on these tests and test them. But the idea is that our first hypothesis, which is a very natural one that a lot of researchers make, given that how high profile this tunnel building process is actually false. It's not true for the whole game. So we can actually conclude through this that the temporal association, which is a formation of a tunnel followed by higher saliency, does not generally imply causal dependence, which is what we as researchers are trying to understand.
I have a question, one practical question. Like, how do you come with this idea of okay, this is the hypothesis maybe somebody else has stated, and these are 46 clean and these are 40 explanation possibly around it. So you can take this 40 sets. But how do you come with the the perturbation or whatever I call it perturbation, but anything like the counterfactual things, like I have to move to the left, I have to move to the right. Like, how do you decide on that? Is it like a decision by you, or is it how do you basically come with like, okay, this is shift right, I should do shift left also, and is there may be any other things also, maybe it's not working at particular shift or something. Like, how do you
Yeah.
decide or roughly think about like what changes I have to do to test this explanation, validate it?
Right. That's a good question. Again, this is something that we have to do on our own. And so there's no way to do this automatically at this point. We would love to automate this in future so that it's much easier to test something like this. But given that these are semantic concepts that we're dealing with and it changes per game, we can make up like a lookup or example intervention that one could do. But it really depends on the type of things you're looking at. So yeah, it is up to you. But again, the idea is that as scientists, we need to be testing these things better.
I also have a question real quick.
Yeah.
So I was just wondering if there's been any research into whether networks themselves can provide some kind of response or explanation for their own actions. I don't know how that would exactly work, but.
Yeah. So there are one other type of saliency maps that are inbuilt into the model during the training process itself. These are all post hoc methods, but there are those, and they do something similar. I think a lot of the work that I've seen in explainability in terms of the model explaining itself has been through counterfactuals. So being able to assess how the model would performs in this scenario versus if we change something slightly, how does it react? And so saliency maps are doing exactly that from the image standpoint, but you could do something similar like that in any other domain that you can think of. So those are there, and there's a lot of existing literature that does that, but we're looking at images here, so hence saliency maps.
Cool, thank you.
Any other questions?
I don't have a question, but I have a comment. There is something similar people has done in NLP, which is attention is not explanation, and there's one more follow-up: attention is not explanation. Maybe you can look at. I think they evaluate same kind of problem where model give attention has explanation, but actually it's not. And attention is somewhat similar to saliency. I feel
right. Exactly. Yeah, exactly. Yeah, I am familiar with that paper. It's exactly that. And a lot of this similar work has been done in computer vision as well, because saliency maps were first used there. But the thing with DeepRL is now it has an additional temporal aspect that you're doing this over time, and you're trying to not just know why the agent gave this label to this image or in classification, but you're trying to know what the behavior is over multiple frames. So it's a little bit more, I would say it complexifies things because we have this temporal aspect. Okay, so let's look at another example quickly. This is a saliency video of a DeepRL agent playing the Atari game Amidar. The agent is in yellow and the goal is to traverse the board without hitting any of the enemies. So as we can see, the agent is always in yellow, is always salient, but enemies in pink are salient at varying times. So we can hypothesize that the agent has learned to avoid enemies close to it, or has learned to identify enemies close to it, resulting in successful avoidance. So to test this, one thing we do is we're very simple. We look at just the correlation between the distance of each enemy to the player and the saliency on the enemy. And this is sort of a textbook example. There's no correlation between the two. It's a blob of scatter points, and we also do a linear regression on it. And again, there's no correlation between the two. So this is very simple. We just look at the data and we plot it. We don't do any intervention. So there's no correlation. To further examine this, we intervene on enemy positions by moving the enemy closer and farther to the player. And the idea is we would expect a higher saliency for enemies closer to the player. But again, the plot suggests that there's no substantial correlation and causal dependence. So from this, we can actually conclude that experimental evaluation is necessary to avoid spurious correlation. In other words, spurious correlation can occur very easily in two processes, in this case, correlation between the player-enemy distance and saliency. And there has been a lot of work in psychology suggesting that human observers are susceptible to identifying spurious correlations. So again, the key point, it's very important to test your hypotheses.
I have a question. So the distance here is the distance in terms of the like the ways to reach the player. The enemy can reach the player. Okay.
Yeah.
Okay.
Yeah,
So two mean like he has to travel two distance somewhere. The minimum distance, there are multiple part to go to the player. The minimum, the shortest part to go to.
that's right. That's yeah. Okay. So let's conclude the paper at least. In conclusion, what does this exploratory non-explanatory thing do? Here we're just saying that saliency maps alone are not reliable tools to infer explanations. And instead you have to use it with other supporting tools or test your hypotheses. And that's exactly it. They're rarely tested experimentally, despite being widely used. And so we propose an intervention-based experimentation as a primary tool to evaluate the hypotheses. And having such a framework is good for developing testing hypotheses that are more specific and falsifiable, and hopefully even make these models better. So before I move on to the next part of the talk, any questions? Okay, this is paper. I have a QR code. It's on the last slide as well. So if you really want to scan it, I think that will be the time to do it. We'll talk about privacy preserving machine learning next. So going back, we looked at a little bit of, you could say IoT with autonomous vehicles. Now let's look at mobile computing. So mobile devices are very popular. I read somewhere, I don't know if this is true, but 97% of the world's population employs them in some ways, mobile phones. And smart mobile devices are often used in various ways, very unique to the user, to offload or assist human thinking. That has resulted in a plethora of user-specific applications in many, many domains, including entertainment, healthcare, travel, education, and banking. And the primary goal is to assist humans in day-to-day tasks. A subset of these applications is something called context-aware applications. These are applications that collect context about the environment, which is basically defined as any information that you can characterize interactions with the environment or the situation of an entity. And they provide they provide back some service. So for instance, with Google Maps, you have a centralized server, obviously. A Google Map can share the current location, your timestamp, maybe historical trajectories of where you've been, and it can offer back some service like the ratings of a place you're at or where you're going, or reviews or photos or prices, things like that. And so Google Maps is collecting temporal and spatial context. Now, these context-aware services are thriving not only on using the correct context, but also predicting future context. And by predicting future context, you can prefetch content like ratings and reviews, or you could provide recommendations based on expected future mobile behavior. So for instance, a mobile application like this can predict a user's next location and then provide recommendations about when a restaurant is closing and future traffic predictions. For instance, this is from my personal example. Whenever I plug in my phone into my car, Google Maps always tells me, okay, it'll take you 10 minutes to get to work. And how does it know I'm going to work? It's because it's doing next location prediction at that very moment. So how do we do this next context prediction? Again, deep learning, going back to our theme, you can use deep learning to do that. So to do that, you can have, what you can do is you can transmit data of multiple users to some centralized server, process it, and come up with a global model. Now, the idea behind using global models is because for deep learning, as we all know, you need a lot more data. And so a single user's data might not be sufficient. And along with that, these models tend to be more robust and more generalizable because they have patterns of many, many users. However, at the same time, as we're going to more real-time processing, they can be computationally inefficient with higher data bandwidth and, latency costs. And there might also be less capable of capturing specific user patterns due to the unique ways in which users employ these services. So what's the alternative to this, you may ask? And as many of you might guess, it's personalized machine learning models. So you can not easily, but you can personalize a general model to cater to the behavior of individual users and make it more user-centric. And one way to do that is you can take the data of a user, use an existing global model that you maybe developed or trained once, and use that to do some personalization and come up with a personalized machine learning model for that specific user. Now, how do you do that personalization? That's we're not going to dwell a lot into that in this talk. I've been looking at a lot of transfer learning based methods to do that type of thing, and there's a lot of existing work on it as well. But we're going to be talking about privacy, so let's move forward with that. The idea here is that you can do this whole process of personalization on the device itself, on some edge node. And if you do that, the data is kept local and the model is only shared on the centralized server. So the data is, stays on the user's device and only the model is shared. Now this has perks like the content is tailored for individual users. It's also privacy preserving training because now it's not prone to differential privacy based attacks. However, what we're trying to look at here is whether you can still leak private information by exploiting a trained ML model. So you do this whole process, but is there a way that you can trained personalized models can they be exploited to leak private information despite being trained locally? So that's the key question here. So that leads me to the next piece of work, which is privacy implications of personalized machine learning models in context-aware mobility applications. This work is in preparation. We hope to submit it very soon. And what we're doing in this work is we formalize inference-based privacy attacks on time series personalized models using model inversion. We empirically analyze under what circumstances these attacks thrive to exploit location-aware applications, and we propose a robust solution. So before going into this, let's talk about model inversion, which is a existing machine learning attack. The goal here is to determine values of sensitive features in the data using output of a trained model. So say you train a model, you have some data, train a model, you get some output. Now, assume you have a data point with n features, f1 to fn, where f1 is a sensitive feature. Now, you're assumed that you have an adversary that has access to DI, this data point, everything except F1. So the adversary knows all the non-sensitive features and has access to the model. It basically has black box access, and it also has some prior knowledge. And the goal for this adversary is to detect what F1 is, what the sensitive feature is. And this is a very simple scenario. How we do that in practical domains is a lot of people have been working on this. A very simple scenario just to show you how this works. So what you can do is the adversary can actually query the model and it can see the output probability. And essentially, if F1 can take two values, it can plug in those two values and basically pick the sensitive variable, the sensitive value that maximizes the model's confidence. So while these attacks have been studied in the machine learning context, we formalize and apply them for time series models common in location-aware services. Question? Yeah. I can't hear you.
Yeah, so I understand this model inversion, so formulation in general, but if you're just the framework of the setup you had on the previous slide, where you were starting with this general model across all the users, and then you're trying to tune it based on your personal data to your personal model. I don't understand what information is leaving the phone, right? What information or operations or queries would adversary have access to that would even give them any sort of potential to do these sort of model inversion or any other sort of attack?
Great question. So I'm actually going to be talking about this on the next slide, but actually let's head over to the next slide. Maybe it'll make more sense then. Oh, the slide after this. So in this case, we're particularly looking at mobility prediction, which is and specifically next location prediction. So let's quickly look at what we're doing here. We have the sequential data, say at each point in time, you have this sequence of data which contains duration, entry time, location, and day of week. So to answer questions like, where was I on this day at this time, and how long did I stay there? And what this model, general model or personalized model, is doing is using the previous two sequences to predict the next location. And in our work, we're using LSTM to do that because they are good for predicting sequential data. And this is a very simple scenario. Again, we're predicting, you can also extend this to predict trajectories of data by iterating this process. And that's something that someone in my lab is actually working on, or has worked on. She has a paper on this. So going back to the threat model, what we're looking at in this work. So say you have a bunch of contributors who are used to train a multi-user machine learning model, MG. Say you have a single user distinct from these contributors who has their own data, and they can use MG to build a personalized model, MP. Now the assumption is they have a local device capable of handling AI-intensive tasks. And then you have your host. Now the idea here, going back to the question that was asked, the host can have access to both MG and MP. Now the reason for that is because the host is actually providing some sort of service, the user has to be fine with them predicting the next location. That's something the user expects them to do, to give them tailored content. So the host or the host of the application can actually have access to MP, and that's what's leaving the local device. And this, again, this host can observe the model output and associated confidence scores to, again, provide service for future context. We can also assume that there's an outsider who somehow may have access to the personal model MP, maybe it leaks, and some prior knowledge. And this prior knowledge in the location domain that we're looking at can be easily accessible through things like mobile cookies, third-party applications, or location-based social networks. And the goal here is to determine, and so here, what we can think of is the host can be an honest but curious adversary, where they're doing the right thing, but maybe they're just trying to know a little bit more about the user. And there you can also have an external adversary. The goal here is to learn historical mobility patterns of users through their personalized models. Now note that this is privacy leakage because the user is not expecting them to know this information. The user is not expecting them to figure out where they were in the past. And this also has problems when you're doing this in terms of, for instance, I think it's the FAFSA, it might be, no, oh my goodness, I forgot the name of it. But in school, basically, if you're in college, your parents actually don't have the right to know whether you were in class or whether you were X square. That's actually a law. And so if you have something like this, you can do that. So there's some implications of this. So the adversary here is trying to learn historical mobility patterns. So the proposed attack is, there's two parts. One is because we're looking at time series data, we're saying this adversarial access is limited by time. That is that at each point in time, so we have a bunch of adversaries, at each point in time, the adversarial knowledge will change or will depend on access to the model, some prior knowledge, and input and output of the model. So for instance, with adversary A1, if it doesn't know the sequence xt-1, it doesn't know any feature at xt-1. And if it knows xt-2, it knows everything at xt-2. So the access is limited by time. And in this case, we have the first two adversaries are very simple ones. They have access to a one or the other previous sequence. Again, it can get that through various means like we discussed previously. But what's more interesting is A3 and A4. So the goal here is to determine these locations. So just build possibly a trajectory of where the user has traveled in the past. In terms of methods, a very simple way to do this attack is brute force, where you enumerate over all possible values of the sensitive feature. That is often extremely time consuming, and as you'll see in this application specifically, it takes forever. There's also gradient descent, where you can just reconstruct the input using the output and a specialized loss function that focuses on maximizing the confidence of the correct output, because you know this LT at each point in time, based on the adversarial knowledge. And then we also propose this time correlation method, which is basically using the dependence between features to minimize the number of iterations. So it's like brute force, but the idea is that if I'm presenting at the Grouda Center for Data Science at 12 o'clock, anything I do before that will be before 12 o'clock within some time range. So if we make assumptions like that about each of these features because of this time aspect, we can reduce the complexity of this attack by a lot. And as we'll see, we'll show that quickly. So moving forward, oh, sorry, go ahead.
So why do you think that the model will have access to MP, even prediction to MP? Because like I agree, like there may be third-party cookies or somehow it's getting access, but that's the whole point. Like MP is a personalized model, so it should work. My personalized my settings is, for example, if I search for something, what kind of results it shows, or what YouTube based on my past history recommend. That nobody should have access or able to get that information because it's personalized. That's the main point of MP. Why do you think the adversary could have access to that? Where things can go wrong? Can you give some example or something?
Yeah, so the idea here is that the adversary is the one that's providing this service, right? Like for instance, if YouTube is doing personalized recommendations, to make their system better, to make their models better, if they have access to this MP, they can do some testing and eventually make it better. That's the whole goal of having these applications. And so there could be many, many reasons why they would have access to MP. One is, of course, to do some debugging or testing. The other could also be, there has been scenarios like mentioning federated learning. I don't know if anyone's aware of that, but where you're trying to use that personalized model to then make a global model out of it. So there's many scenarios where this could happen. And it's not rare for some service it might be rare for some external adversary to have this information. That it really depends on whether somebody hacked your system, or whether there's a leakage from the server side, from the host side. But the host definitely has access to, can definitely easily have access to this model. And again, these are things, I've been thinking more and more about privacy, and these are things that sometimes are written in these terms and conditions that we never even bother reading. We're taking it one step at a time. So the edge computing allows us to do computation on the device itself. So the data is not going to the centralized server, but at the same time, if we provide this model for some service, then can we still leak information about our data, past data?
Makes sense.
Okay, so quickly, the experimental setup, we actually look at a campus scale Wi-Fi data set, and that's where I mentioned the parents finding out about where their kids were. We look at only on-campus students using some heuristics, and we look at two different spatial scales, building level and AP level. Now, AP is access points. So there's about 3,000 access points at UMass, and there's about 150 buildings. So we use 200 users. Now note the spatial levels, it's a very big domain size. Even with buildings, if you're trying to predict which building you have been to among the 150, that's a very big domain size. And so jumping to access point level is even bigger. So in this work, what we're trying to see is how does a low-level spatial versus high-level perform in terms of privacy preservation. So I'm going to present some preliminary results today. This is how the attack performs. Again, we have our attack method, which I talked about, brute force optimized, which is gradient descent, and this time correlation method. And we tested on 100 distinct users at building level spatial. building spatial level. So we see that the brute force method performs really well, along with this time correlation method that I talked about. But the key part is this time correlation method is substantially faster. It's 75 times faster. So applying heuristics that finds these correlations between these features over time is substantially faster. Now note in the bottom here, the x-axis is K, which is basically saying that it's basically top K predictions. So if we predict the top 3 locations is the actual location among the top 3. If we predict the top 5 is the actual location among the top 5. So the idea is, of course, it'll grow as we increase. But the interesting part is there's up to 80% privacy leakage for top 3 prediction, which is still pretty large for something like mobility. The reason the gradient descent doesn't work as well is likely because of the number of locations. It's performing less than 25%, which is pretty bad. But it's likely due to the very large domain size that we're dealing with, and because of that, it has an inaccurate reconstruction. It's not able to reconstruct the historical data as well. So the proposed solution, I'll just quickly go over this because I want to get to the last slide, is basically we use some sort of a privacy tuner that scales the output before the softmax layer. So this type of attack thrives in the fact that the confidence scores are sensitive to each location. Now, if we apply this tuner T, and basically before applying the softmax layer, we divide the logits by this T value, then the confidence scores will be very highly insensitive with respect to the output. And note this is very similar to the notion of temperature in deep learning, which is often used to control the randomness of predictions. And then in this case, what we're suggesting is the user can pick this T value, this tuner, and keep it private. And this is only used at inference time. So T again changes the sensitivity. So it either makes all the confidence scores highly sensitive, either close to 0 or close to 1. The host can still gather the top K predictions, but it's not going to be, the confidence scores are going to be fairly insensitive. So quickly showing these results, these are 2 personalization methods that were tried. These are both transfer learning based. And we're able to reduce privacy by 22 to 30%. As we can see, as K increases on the x-axis in both types of models, there's less privacy leakage. Note, even 22 to 30% is fairly high, given that the data is fairly skewed. For instance, when I travel to campus, I only visit a certain subset of locations more than the other ones. I'm always, for instance, in the CS building versus, I could visit campus center once in a while, go to the cafeteria, or go to a dining hall or something like that. But it's a skewed data set. The other thing I want to show is the impact of this temperature privacy tuner thing. So as temperature decreases, the privacy leakage decreases as well, eventually flattening out. And the key part is that it will differ for each user and for each spatial scale. And this is for building level that I showed everyone today. So the key takeaways here are that personalized models are capable of leaking private information despite being trained in a privacy preserving manner. And the nature of these context-aware applications result in more leakage of private information than expected by user. So I'll quickly talk about the future of machine learning in modern distributed technologies, and I'll conclude the talk. So my work, as you might have noticed, spans over machine learning, edge computing, cloud computing. In machine learning, we want things to be perform well, so high performance, like I described before. The other part of it is application-specific utility. So a lot of existing work in terms of generalization, fairness, things like that, has been on visual data. And that's not a problem. That's great because now we understand these models and visual data much better than we used to, say, 10 years ago. But there's a differing set of complexities for non-visual data. So for things like if I'm looking at IoT or mobile computing, there's a different types of, these systems have different sets of different complexities essentially. So my prior work focused on deep RL applications like autonomous vehicles, and now I'm looking at IoT and mobile computing. And this basically has area to grow multi-domain work. With cloud computing, we want something that's low latency, has low latency, something that's privacy preserving and secure so that we're not leaking a lot of information to the cloud. And edge computing, it's a new paradigm of distributed systems, and we want it to be using low resource and highly efficient. All of these things are interconnected, so we can think of, I'm going to pose a few questions, think of these as new tasks. So from the machine learning and cloud computing standpoint, we can answer things like, how can we develop privacy preserving and secure machine learning algorithms? We already have these great algorithms that have been traditionally are being used, but how can we make them more privacy preserving and secure? One option, and this is something that I've been working on also, is leveraging distributed deep learning to build novel solutions for this type of high performance machine learning. And distributed deep learning, things like split learning, federated learning, we can employ those types of things. From the machine learning edge computing standpoint, how can we develop, we already have these great machine learning models, how can we develop low resource yet efficient machine learning algorithms? Is there a way we can make them use less data, or is there a way we can make the complexity of the model less itself? And in this domain, I'm working on developing robust models for personalized modeling. I briefly mentioned that today. And lastly, in terms of cloud computing and edge computing, what is the ideal integration between edge and cloud? The edge computing hardware is increasing, is growing, but is there an ideal integration that we can do to get all of these things in one? So adapting edge computing systems to stimulate and optimize multiple goals is something that I'm also interested in doing in future work. So to conclude the talk, the future of AI will be more personalized, distributed, privacy preserving, generalizable, explainable, all those good things that I talked about. And I'm continuously thinking about deployment of ML in real world systems. And these evolving requirements present novel research opportunities and challenges in both AI and its systems. And finding the ideal balance between edge and cloud for maximizing performance of machine learning models is what I'm very interested in doing. So thank you so much for listening. I hope you guys enjoyed the talk. I'm open to questions.
So thank you very much for the great talk. So for giving this overview of these areas and kind of, you know, and how this interacts with these different problems that are, you know, that are so that are so making it part of data science. So I want to see if the audience has any questions in the chat, or you can raise your hand. So I've got one other question on so the privacy preserving stuff. So you start by saying this model about how you are going, how the point of the personalized model is that you can run the machine learning on the actual phone, and you can build the model on the phone. So why did, so if I'm YouTube and so I want to make a personal like recommendation on a video, then is it not possible for YouTube to do that entirely on the phone? Or is it that in order for YouTube to do this, you have to actually pass the model back up to the cloud for YouTube to run through its entire list of videos to make the recommendation? Or maybe is it like YouTube can send a bunch of possibilities and then it observes which one you actually watch, so it's still learning something about you anyways?
Right. Yeah, it's a good point. So one of the problems, and it's not a problem, it's just things that are evolving over time, is that these edge computing hardware is limited. It's not able to do more than what a cloud would do. And so we do have things that are meant for AI intensive tasks now, these edge computing softwares, or it's not software, hardware. But it's still not in the it's still not as well as what you would get if you're doing it on the cloud itself. So there could be things there, but as we move forward, because of how fast these things are evolving, this might not be a problem. Maybe and eventually what's going to happen is everything's going to happen on the device itself. And hence our phones, like I have an iPhone, my phone has been getting heavier over time since the past 3 years because of the fact that it has so many more things on like hardware on my phone.
Yeah, so great. So, okay. Yeah. So I think that makes sense. So, so when you first described the model, I'm like, oh yeah, just the model itself should be safe. But yeah, but I can see where these issues are now. So great. So Lynn, you've got yourself off mute. Maybe you have a question?
Oh, you caught me, Jeff. This is a great talk. Can I go back to the first part of your talk on the saliency maps? Now, I'm thinking about this evaluating counterfactuals and doing experimentation. And one of the things that strikes me is that actually kind of a different way of looking at this, or kind of a deeper dive, is to think about kind of borrowing from another discipline, like the potential outcomes for reinforcement learners who are exposed to different conditions. And in a sense, what you'd want to do is be able to have, you know, in theory, you'd have exactly the same reinforcement learner who was exposed to 2 different versions of the environment that it was in. But the environment affects what the reinforcement learner learns, right? So can you really have that? Can you really have, assuming that you could do that, can you actually really argue that the only difference between these 2 reinforcement learners in the 2 conditions is kind of the nature of the display at the time that you're evaluating it?
Right. Yeah, that's a very good point. We didn't actually attempt to use the potential outcomes framework for this. It could be very well be applied. One of the issues I think with that is because we're looking at these individual like semantic concepts, right? There will be causal graphical models visually and the way that they work. It's very easy to apply these individual treatment effects versus in the potential outcomes framework, it's not as clear specifically with this domain. So yes, it's a very interesting thought, and I think it is possible. But that's not something that we tried.
Yeah, thanks. Yeah, it doesn't strike me offhand how it would be even feasible. But ideally, if we could do that, that would be kind of even a stronger argument for the kind of causal conclusions that you'd make, right? About the game state, which is really kind of like a collection, like a latent variable domain, right? From the standpoint of how salience maps are currently being used.
Right. Yep. And I think it would even be faster because of, I think it's the way that potential outcomes framework works.
Yeah. Thanks. This was a great talk. I really appreciate it.
Thank you.
Yeah. So if we don't have any more, so questions, let's thank the speaker one more time. So.
Thank you.
Great. So thanks for the great talk. So yeah.
Thanks.
Awesome. Thank you so much for having me. I really appreciate it. And please feel free to email me if you have any questions or just want to chat. I'm happy to do that. Thank you.
All right. Thanks. Bye, everyone.